Hi everybody, welcome to this video where we're going to talk about the surface expression of active faults. So you probably know that as tectonic plates move past each other slowly and steadily, it's fractures in Earth's crust, called faults, that allow those plates to move past each other. They're accommodating that motion. So the job of an earthquake geologist is to identify where are those faults, what's their orientation, how fast is the motion along those faults, and how likely are they to produce earthquakes. So in this video, we're going to talk about how geologists actually identify these different types of faults by studying their shape or their morphology in the landscape. So here's the outline. First, we'll introduce three types of faults, and we'll talk about how they intersect topography. Then we'll look at the details of strike-slip faults, normal faults, thrust faults, and then we'll finish by looking at extinct faults and how we can actually still often see ancient faults even if they're no longer active. So there's three basic types of faults. The first type is a strike-slip fault, and this tends to be vertically oriented in the crust, and we tend to have the blocks moving past each other side by side, essentially in a lateral motion. The next type occurs under a compressional environment when the plate is being squeezed, and this is called a reverse or a thrust fault, in which the hanging wall is being pushed up and over the footwall along the fault. And the third type occurs in an extensional setting where the plate is being stretched, and this is called a normal or sometimes just an extensional fault. And so in this case, the hanging wall is being dropped down relative to the footwall and allowing the crust to be thinned or stretched. So before we go on, it's important to know a little bit of basic fault vocabulary. So for example, the first thing to know is the fault plane. So that's shown here. This is the actual planar feature that's allowing the two blocks to move past each other. And this extends deep, 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 many kilometers into Earth's crust, and sometimes it actually touches or intersects the surface. When it does so, we'll usually call that a fault scarp or escarpment, usually a steep surface or a step in the landscape where you can actually see where one block has moved relative to the other block. We already touched on this, but typically we'll call the block that didn't move, which is usually an approximation, as the footwall, and then we think of the block that's moving as being the hanging wall, although usually both blocks do move. So if we follow this fault scarp across the landscape for long distances, we get what's called a fault trace, and that's shown here in this map. This is a map view depiction looking down on the surface. And fault traces help us understand where offset might have occurred along the fault. And sometimes we'll have multiple fault strands or multiple scarps that are close by each other, and we'll call that a fault zone. Great, so now you're ready with some vocabulary. Let's talk a little bit about how faults can be traced across the landscape. And this depends a lot on the orientation of the fault plane relative to the actual topography. So in the case of a strike-slip fault with a vertical fault plane, that's shown here as a brown line, that fault plane, and you can see that regardless of the topography that it's intersecting, a vertical fault will always make a straight line across the landscape, right? Even as it runs through this river valley. That contrasts with something like a low-angle thrust fault. So in this case, the fault shown by the brown line is dipping maybe 20 or 30 degrees from the horizontal. So what that means is as that plane, okay, this is a planar feature, as that plane comes up and intersects the surface, that intersection appears to be a line where it's intersecting a flat surface. However, once you go into some topography, we see that plane, the intersection of the two planes, steps back like this and then steps back up as you go up the other side of the river valley. So we can think of this as being more of a contour shape. So the lower the angle of the fault, the lower the dip, the more it tends to follow contours of the topography. And that's one way that we can actually tell what type of fault it is. Strike-slip faults are almost always making a straight linear trace, whereas thrust faults tend to contour with the topography a little bit more. Okay, so let's go now into the morphology of specific fault types. So our first example is that vertical strike-slip fault. So here is the fault trace. These symbols are meant to be arrows. This is the tip of an arrow that shows this block is coming towards us, and this X shows this block is going away from us. So this would be a right lateral strike-slip fault, and we have a lot of topography associated with it. Most importantly, we have these linear valleys. Okay, very linear valleys tend to have a trough associated with them, and that linear valley is formed by a variety of features. One is called a shutter ridge right here. These are ridges that tend to push up along the fault. And as this block here moves to the left, you can see this ridge has been slid and blocked an active drainage right here. And so that's why we call it a shutter ridge. It's slid across and blocked the drainage, much like the shutter of a camera closing across the lens of a camera. As that happened, this whole drainage was also offset. This river was coming out here and continuing. Now that continuation is now here. This is literally an offset drainage channel. It's been moved across the fault. Of course, we also have fault scarps. Another important thing that we're going to see here is springs. Many faults, including strike-slip faults, because they are zones of fracturing and broken rock, tend to allow water to come upwards from the deeper crust and reach the surface. So we often find springs along fault zones. So let's look at some examples of this. Here is the San Andreas Fault in Southern California, and you can clearly see this fault is making a very longitudinal linear trace. It does have a trough or a valley here. This whole thing right here is a shutter ridge that has moved from left to right, and you can see this ridge has appeared and actually blocked outlet of this river system. This river system was coming here. It's been blocked by the shutter ridge, and now it's deflected, forced to go around like that. So there's a lot of other features here as well, but those are some of the basics. There's another example. This is the San Andreas Fault down near Palm Springs, California. And what we see here is a linear array of palm trees that are marking the exact trace of the fault line. Reason being, this is essentially a series of springs, and the palm trees are able to grow because of those springs that are occurring right along the fault line. Okay, so let's move next to extensional or normal faults. So just to remind you, in this case, we have the hanging wall that's been dropped down relative to the footwall. Okay, this creates a number of different features. One important feature is called triangular facets. This is where ridge lines are essentially getting truncated and leaving this very unique kind of triangle-shaped escarpments. Another important feature of an extensional or normal fault is because the footwall is being dropped down, we're creating a lot of accommodation space for sediments to accumulate right here, essentially along the fault scarp. So here we're calling those syntectonic sedimentary deposits. We're accumulating a lot of sediment here as this block drops down. And a final feature of normal faults is these pervasive alluvial fans. So we very commonly go from having rivers that are confined within relatively narrow upper valleys. As they come across the fault scarp, they're now able to expand onto this downdropped block. And as they do that, they create these features called alluvial fans. So we'll often see a lot of sedimentation essentially at the fault scarp. So here's some great examples of those features. This is the Weber segment of the Wasatch Fault in Utah. Of course, we have our triangular facets all right here. So this is obviously the footwall, this is the hanging wall down here, and this is the fault trace. Keep in mind we have our confined drainages here, and then as they come out, they create alluvial fans. So all these neighborhoods are actually built on alluvial fans. And when you combine all of this, we get another diagnostic feature called a wineglass canyon. We get these canyons that have these big, broad, bowl-shaped upper parts, and then the river comes out and pops through a little incised gorge. That's the stem of the wineglass. So we often see these wineglass canyons. And another note on extensional faults, they don't have to be just one single fault. Quite common we'll see multiple extensional faults working together to create what's called a Horst and Graben topography. So if you look at this, we have multiple normal faults. This whole block is being extended from left to right off the sides of your screen, and that extension is being accommodated by lots of these little faults. And you can see this pair of normal faults right here has actually dropped a block down, and we call that a graben. And then the footwall block that's been left behind we'll call a Horst, and then we move right over into another graben here. So often we'll have some master fault. In this case, this would be the Wasatch Fault that we just looked at. Here's our alluvial fan, our wineglass canyon. And then as we come off of that, we may have whole systems of sometimes smaller extensional faults that are making a Horst and Graben topography. So an example of that is the East African Rift Valley in Kenya. So here's a satellite image looking straight down on the Rift Valley. Here's a lake for scale. Here's a little green river valley for scale. And each of these shadowed lines is actually a fault scarp, okay? So you see we have dozens of different fault scarps in the valley here. And there's also a bunch that are facing the other way. This one right here appears to be facing to the bottom right of your screen. So again, this is a Horst and Graben topography as extension occurs from the top left to the bottom right of your screen. So we'll move towards the finish line here talking about the morphology of thrust faults. So note that thrust faults, the hanging wall is being pushed up relative to the footwall. If that thrust is at a relatively low angle, we'll see the fault trace actually contouring up and into some of these valleys a little bit more than the other ones did. This does share some similarities to an extensional fault in the sense that we have one block that's essentially moving upwards relative to the other block. And so that obviously creates, again, accommodation space right here up against the fault trace. So we have more syntectonic sediments, we have more alluvial fans, and we'll often also see signatures in our river profiles, such as nick zones or other terraces that are being produced as those rivers cut down in to the hanging wall block. Another common feature of thrust faults is folds. So as the hanging wall moves along the thrust block here, we see sediments that are in fact folded like this. And it's also very common we'll have multiple thrusts breaking out in what's called a fold and thrust belt. So in this case, as this fault became mature and slowed down, a new fault or an incipient fault broke out towards the foreland, and you can see an anticline fold beginning to grow above this fault here. So a great example of this is here in Central California. We have the Tehachapi Mountains growing over an essentially emergent or more mature thrust fault. And then a new blind thrust has broken out more towards the foreland and has an anticline growing above it. That's Wheeler Ridge. So to wrap up this video, I want to just quickly point out that everything we've talked about today has really assumed faults are still active and still shaping the landscape around them. However, it's important to note that even once faults become inactive, we often can still see them in the topography, especially if they have juxtaposed two different rock types. For example, a hard metamorphic rock might get juxtaposed against a soft sedimentary rock. Over time, that soft sedimentary rock then erodes away and reveals often linear fault traces, even though they're not active. So some great examples of that are here in the Champlain Valley. Here's the Adirondack basement, some ancient metamorphic rocks. Here's the Green Mountains, also ancient metamorphic rocks. This is Lake Champlain coming down the middle in purple. And we can see some pretty interesting things. Here's Lake George. So this is a graben. This very linear feature right here is a fault, extensional fault. Here's another extensional fault. So these are not active. They've just been accentuated in topography. Here is Split Rock Mountain, which is another set of basement gneiss rocks, and a linear fault trace right here where some of these softer sediments have been dropped down off of that footwall. So to summarize, the map view pattern of a fault trace depends on how the planar fault plane is intersecting with the topography. For strike-slip faults, that tends to be a linear intersection because the fault plane is almost always vertical. They're also characterized by longitudinal valleys, shutter ridges, and offset rivers. Normal faults tend to be characterized by those triangular facets, wine glass canyons. We also see tilting and sedimentation on the footwall. Thrust faults, because they can have a low dip of the fault plane, often will give us a non-linear fault trace as it intersects topography. And they also often will have growing folds growing over them. Sometimes they'll be thrust up over their own footwall sediments. And then finally, keep in mind that differential weathering can still highlight faults even if they're extinct. Thanks so much for listening, and have a good day.